In this video, we're going to do some practice problems relating to left and right Riemann sums and looking at estimating distance traveled. In our first example, we're going to look at time t, given in seconds, we're given the velocity function of an object, negative t squared plus 40 meters per second. We're going to look at the interval 0 to 6. We're going to use delta t equals 2, so each time interval is 2 seconds, to estimate the distance traveled over this time. We're going to find the upper and lower estimate, and we're going to average the two. The reason why we didn't say left and right estimates is because we don't know which one is going to be up, which one's going to be lower, until we think about if it's decreasing or increasing. So let's do the left Riemann sum. And actually, before we do that, I want to just look at this interval here from 0 to 6. If delta t equals 2, then we have 3 intervals that we're going to look at. Right, if delta t equals 2, then we have n is equal to 3. We're going to look at the first 2 seconds, the middle 2 seconds, and the last 2 seconds. So now let's think about our left Riemann sum. We're going to use the left endpoints in each of these. That is, we're going to look at v of 0 times delta t plus v of 2 times delta t plus v of 4 times delta t. We're using the left endpoint on each of these subintervals. And we're given the velocity function. We could just say v of 0 is going to be negative 0 squared plus 40. Delta t is 2. 2 is going to be negative 2 squared plus 40. Delta t is 2. And here we have negative 4 squared plus 40. Delta t is 2. So overall, it's going to give us 40. And here we can actually maybe take out a 2 from all of these terms. We can have 40 plus 36 plus 24, all of it times 2, which is going to give us total 2 times 100, or 200 meters traveled. Now let's think about the right Riemann sum. Here, we're going to use the right endpoints on all of these. We're going to use the 2, the 4, and the 6 as our endpoints. And that's going to give us v of 2 times delta t plus v of 4 times delta t plus v of 6 times delta t. And again, that's going to be negative 2 squared plus 40 times delta t plus negative 4 squared plus 40 times delta t plus negative 6 squared plus 40 times delta t, which is 2 in all of these cases. And again, what we could do is we could bring out the 2 out in front of all of these, and we get negative 2 squared plus 40 is going to be 36. Negative 4 squared plus 40 is going to be 24. And negative 6 squared plus 40 is going to be just a 4, negative 36 plus 40. So adding that all together, we get 2 times 64 which is going to be equal to 128 meters. So we can say that distance traveled in either of these, all right, this is about distance traveled. What we could do is we could look at the average of those. That's going to be maybe a better estimate for the distance traveled. And that's going to be 200 plus 128 divided by 2, which is 164 meters. Maybe that's a better estimate. Lastly, let's think about how good of an estimate is this. We have that f of b minus f of a times delta t. That's going to be v, in this case, v of 0, not v of 0, sorry, v of 6 minus v of 0 times delta t, which is 2. And that's going to give us a total of 72 meters. That's the difference between our estimates. Note that we could have done that by just saying 200 minus 128. We already did all the work, but we could have done that at the very beginning. And that gives us an idea of exactly how good of an estimate we would have. So let's do something with this. Let's say instead that we did a different time interval. So I'm going to go to a new page here. Actually, I can go here. We have a picture of this graph as well. So here is v of t, right? And we did 3 different intervals. We had our left Riemann sum to 2, 4, 6. Right, that was our left, and our right Riemann sum used the right values, which actually became a underestimate. V of t is this quadratic here, and the actual area under the curve is that whole thing. All right, so let's say instead, if we used delta t equals 1, that is, n is equal to 6, then the gap in our estimates would be f of 6, sorry, not f, v of 6 minus v of 0 times delta t, and we could use the same values we had before. Sorry, v of 6 we found out to be 4, v of 0 we found out to be 40, so this is going to be the absolute value of 40 minus 4 times 1 is just going to be 36. So you could ask questions like, how small of an interval do you need for your gap to be small enough? And you could kind of fiddle around with those algebraic equations. And it's nice because we're only using really 2 values there, the 6 and the 0. All right, different kind of question. The following graphs here represent the velocity of a particle traveling along a straight line. Find the change in position and the total distance traveled in each situation. So the first thing we're going to have to do is to think about what areas are we even looking for here. We have 4 different situations. So the first one, we have these kind of straight lines. We're saying in the first one that the velocity is 2 for the first 3 seconds, and then it jumps to a velocity of -3. Not a very real world situation, but maybe something like that could happen, an instantaneous kind of change in velocity. But if we have this, the area that we're looking for is going to be from the function to the x-axis, or the t-axis in this case, and we have both a positive and a negative area that we're looking at here. And we're really looking for the area here, and we have nice shapes we can deal with. So this area is the area of this rectangle, and that's going to be 3 times 2, that is 6 units. Whereas this other rectangle is going to be the distance of 2 times -3, or 2 times 3, which is going to be -6. So here, the distance is going to be the 6 plus, we can say maybe the absolute value of -6. Total, we've gone 12 units. But the displacement, the change in the position, is going to be 6 minus 6 is 0. So this is like the particle went forward a bit and then went backward to its starting spot. All right, think about the next one. If we go to the right here, we have a straight line just at -3. That's going to be negative area, but it's a nice rectangle. It's easy to find this area. It's going to be 5 times -3 is -15. So it's like we're going in reverse. So this particle is going in reverse. The distance is going to be just the 15, and the displacement is going to be -15 units. All right, next one, we have a straight line. It's not a rectangle. We're going to have a triangle that we can find the area of. The area here is going to be 1/2 base times height. It's going to be 1/2 times 5 times 10 is going to be 25 units. And that is going to be both the distance and the displacement, since we don't have any negative stuff going on there. So the area of a triangle, we're just finding that area given our functions here. And then lastly, we have this triangle that kind of goes above and below the x-axis. We have this positive triangle and this negative triangle. The positive triangle has an area of 1/2 base 4 times height 8. That's going to be 16. And this guy has a 1/2 base 1 times height. I don't think I actually gave the height. Height should be -2 there. And this is going to be a -1. So the distance is there are 16 units traveled plus the absolute value of -1. That's going to be 17. But the displacement will be 15. 16 minus 1 is 15. So if you're above the x-axis, we have this positive area. Below the x-axis, we have this negative area. If we're thinking about just distance, we're just taking the absolute value of both. If we're thinking about displacement, we are thinking about the signed area. The positive and negative mean something. We're going to look at this in more detail in the next section, and this is all leading up to what we're going to define as the integral, and that's the big kind of last thing we're going to define in this course.